Okay, topik kita pada pagi ini is actually the topic that we need to cover after your cuti. Kita dah habis sampai sini dah. We have covered up until kinematics, linear and angular kinematics, all those displacement, velocity, acceleration, settle. So today kita akan cover topik ini. Ni dah, kita dah laju sikit ni. We are going to cover about kinetics. Okay, ditulis sini application and linear and angular kinetics. But if you take a look at this topic, topic ni foundation of human analysis ni, this one is actually part of linear kinetics. Okay, means that for this week we are going to cover most of kinetics and angular kinetics. So afterwards baru kita cover linear kinetics dekat dalam bahagian foundation of human analysis. Alright, and then if you take a look here at week 9, this is the week after your special festive break. You are going to have quiz 2. Okay, another 10 question objective, and it will be cover the topic that we I think the topic for quiz 1. Mana quiz 1? Quiz 1 is week 6 kan? Quiz 1 week 6. Jadi dia dah cover sampai stability. So for quiz 2, we are going to cover the topic of COG and also linear and angular kinematics, velocity, acceleration, displacement. Yang tu akan masuk dekat dalam quiz 2, another 10 question. Okay, jadi yang kita belajar hari ni dia tak masuk quiz 2 lah. This one is going to be covered in your test 1 later on. Ni, week 11, test 1. Okay, so let's go to the topic. Before we go to angular kinematics, let's see some of the terms and also refreshment regarding kinetics tu dulu. Apa itu kinetics? Okay, so what is kinetic? When you see kinetics, okay, bila nampak je kinetics, the first thing I need you to have in your mind is movement. Kinetic is the thing that is moving. Okay, kinetic is movement. Kinetic concerned with what cause the body to move. Kinetic sendiri movement. So when we talk about concept of kinetic, we are going to talk about the reason why a thing move, a reason why human move, which is force. Okay, which is force. Kenapa kereta tu bergerak? Kereta yang bergerak ada kinetic. Okay, kinetic energy. Benda yang bergerak ada kinetic energy. What cause benda bergerak? Force. Okay. So a force can be characterized as a push or a pull. Okay, a push action or a pull action. And when we talk about force, force have magnitude, force have direction, force have point of application. Ada tiga benda datang, ada tiga datang. Okay, bila kita cerita force, okay, this is, let's say, this is a box, and you apply force, it will cause the box to move. Jadi force sendiri, properties of force, first ni benda ni, magnitude dia. Okay, how much? Magnitude is how much. So the longer the arrows, the larger the force. Ni dalam mechanics lah. Okay, dalam mechanics we can substitute force in arrow. Kalau kita ada dua arrow macam ni, so the longer the arrow, more force being delivered compared to the shorter one. Satu dia ada magnitude. Number 2, dia ada direction. Okay, when you see direction in physics, it talks about this thing, Cartesian coordinate. Move to the right, positive. Move to the left, negative. Move upwards, positive. Move downwards, negative. That is what the meaning of direction of application. And the third one is point of application, where we apply the force. Macam ni ke, macam ni ke, macam ni ke. Because the direction of the force being applied, the point where the force being applied determine the movement of the object. Kalau kita apply daripada A, it will goes that way. Kalau kita apply daripada B, it will goes downward. If we If we apply from C, it will go diagonally. Tu maksud yang ketiga, point of application. If we don't point of application, if we don't have any point of application, means that there are no force being delivered to the object, so no movement is going to occur. Newton first law, okay, inertia. Tiga benda ni, magnitude, direction and point of application. So force being described in terms of Newton, and we can actually find force in secondary method. This one is secondary method by using equation of F equals to ME. Ni konsep asas apa itu force. Okay, so forces, it can be divided into two types. One is known as internal forces, second is known as external forces. Okay, benda mudah. Let's say we have people try to kick a ball. Okay, they try to kick this ball, and we know that when impulse be given to the ball, it will cause the ball to travel. The way you swing your leg, okay, why you able to swing your leg is because there are force being generated at all of these muscles. Okay, force generated in muscle, force generated by muscles. Generated by muscles. This is an example of internal force because it originated internally in your body. Force internal. When you swing your leg and you give an impulse to the ball, okay, you transfer impulse to the ball. This impulse is an example of external force. Force that being transferred from one party to another party. Okay, bila dia transfer force macam tu, that is known as external force, or else the ball is not going to move. Ball tak ada force sendiri. They need external force. Tu dua kategori force. Okay, internal force, force that act within the body. External force, force that act on an object as a result of its interaction. Meaning, they need to have contact. They need to have transfer of impulse. And then only external force is going to presence in the system. Internal and external force. Okay, these are the three Newton law. We have discussed about this one, so I'm not going to go in depth. It's just that the first law, okay, revision, the first law is more towards when there is no force, there won't be any movement, there won't be any acceleration. When we give force, second law, it will cause an acceleration, okay, and acceleration cause a movement. So second law describe the kind of movement that you may have based on the acceleration. Okay, when we apply force, it will cause movement. The movement, the velocity of the movement, the acceleration of the movement is proportional to the amount of force in the direction of the force being applied, and inverse direction with the weight or the mass of the object. The second law. And the third law said that what you give, you get back. Okay, for every single action, there is equal but opposite reaction. Means if you try to jump higher, inflict more force to the floor, so you are going to go higher. If you try to run faster, inflict more force to the ground to push you forward harder. So result is you are going to run faster. So there is no such thing as invest a little and you are going to get a humongous amount. No, you are not going to get something like that. If you try to have something that is big, you need to invest big. In this case, it is force. Okay. And then we have force and torque. Okay, when we talk about torque ni, kita dah mula masuk ke dalam angular, because torque T equals to F D ni, this one is actually force in angular fashion. Jadi dalam case angular, we are not going to call it as force. What caused the rotation? It is torque. What caused the translation? Gerakan tegak. It is force. What caused the leg to move? It is torque. Okay, and most of the time when we talk about torque, it involves motion at joint, because all of our joint move in rotational action since it is involving an axis of rotation. Jadi dia adalah lebih kepada torque. Okay, Lagi satu, bila kita nak faham torque ni, torque is actually force being applied in different direction. Okay, we have a book. Let's say we have a book and we apply force. It will cause the books to skew. Okay, yet this curve movement is still linear movement. To be exact, it is known as curvilinear. Okay, when we talk about torque, it is when we apply force from two different direction. Macam tu. Jadi bila kita bagi dua direction macam ni, what is going to happen is that it will cause the book to rotate at the axis. This is torque. Okay, jadi dalam macam human body, most of our human body is torque because one, we have axis. Two, there are two forces acted upon the system at any given point of time, like our bicep column. So the bicep most of the time is going to pull upwards, and the weight of the hand itself, or maybe the weight of the object that in your hand, will actually pull your hand downwards. But dua jenis torque, two amount of force being acted upon the system in different direction. So this is an example of torque. Okay, so most of human motion involving torque. Okay, it will involve torque. Alright. Itu berkenaan dengan force and torque. Okay. And then in order for you to measure, okay, in order for you to measure forces, there are two ways to do it. One, we call it as direct measurement. This one is the exact figures of the force that being applied during that particular time. Or you can rely on indirect method where we are going to use equation. Jadi most of the time when we talk about equation, there are plus and minus lah. They won't be exact unless you have control everything, or else it just a form of prediction. We can use it, okay, dia tak salah, we can use it, but maybe if you go for direct measurement, the figures is going to be slightly differ compared to indirect. Either way, this is the way for you to find out how much force being delivered or how much force being absorbed by a certain people or things in a period of time. Okay. Alright, this one, yang ini kita dah cover masa topik projectile, if I'm not mistaken. Kita dah cover projectile. So free body diagram is actually part of the projectile, so I'm going to skip this one. Okay, we go to vector algebra. Pernah buat tak benda ni? Do you have any idea about this one? Anybody? Vector algebra, apa sebenarnya vector ni? Ada tiga, ada empat jenis. We have composition and we have resolution. Do you ever come across this one during your diploma level? Ada? Ada, boleh skip lah. Ada tak ada? Ada ke tak ada? Buka mic dulu, tunggu kejap baru cakap. Kalau kamu cakap terus, dia hilang separuh. Do you ever come across vector algebra? Sepi dah. Okay, sepi, menyepi. Alright, tak apa, saya ulang sikit. Vector algebra, first vector. We have two unit of quantification. One is known as vector, another one is known as scalar. Okay, beza dia, compare these two, the beza is only one. Here, we have direction and magnitude. How much, where to go. Scalar tak ada, magnitude je dia. So the first one is known as vector composition. Penambahan vektor. Okay, To compose a vector, first we need to determine the direction. If the direction is equal macam ni kan, kita ada satu campur dengan satu yang lagi panjang, sama dengan apa? If the direction is equal, we know that the answer will also pointing that way. The one that you need to know is actually how long is this arrow. Okay, if we assume this is 1 cm, this is 2 cm, so the resultant vector ni you need to draw a 3 cm. Means that 1 cm force plus katalah 1 cm equals to 1 newton. 1 newton of force plus 2 newton of force in the same direction, because it will result at 3 newton of force. Ni vector composition. Kalau dia ke sana pun sama. Itulah plus. So you need to have how long the total length of the arrow, and that is the answer of it. Ni vector. Same goes if it goes upwards. Atas. So that is the result. Vector. Okay, and if it goes downwards pun sama. Look at je berapa panjang ni. That is vector. So the length of the arrow representing the amount of force in the system itself. Ini kalau the arrow is at the same direction. Okay. Second cases occurs when you have something like this. Satu macam ni, katalah 1 cm campur dengan macam ni. Different direction. Okay, different direction but yet still horizontal. Okay, ini kan. Horizontal, vertical je. Dia belum campur horizontal vertical. Okay, horizontal. If you go like this in equation wise, this one is actually 1 plus ni ke kiri kan, negatif 2. Jadi kalau tak tahu sakit kepala, tengok dia ke kiri negatif, ke kanan positif. So if 1 plus negative 2, you are going to get negative 1. Means, kat bawah. You are going to get negative 1. Means that the resultant arrow is actually to the left hand side. Berapa panjang? 1 cm. Okay. Kita ada ke atas. Kata 5 cm. Plus ke bawah 3 cm. Okay. Berapa jawapan dia? You go 5 plus negative 3. Berapa? 2. Jadi jawapan dia ke atas. Panjang dia 2 cm. This is also a vector composition. Means that if we give force 5 Newton upwards and 3 Newton downwards, what is the resultant force? That is what vector algebra talks about. It talks about the movement of force based on diagram. Okay, ni case kedua, where we have a composition of different direction vector. Okay, the third one, composition, is when you have siapa tekan dengan aku dalam bentuk vektor negatif, apa ni, dalam bentuk vektor negatif dalam bentuk direction ke apa tu, apa yang kamu cuba tanya Ifah? Dalam bentuk vektor negatif.
Maksudnya macam saya tunjuk kan satu ke kanan campur dengan 2 cm ke kiri equal to 1 cm ke kiri. Tapi kan kalau dalam calculation dia jadi negatif 1.
Sekejap. Mana? 1 cm ke kanan,
2 cm ke kiri equal to 1 cm ke kiri.
So kalau satu campur dengan negatif 2 dapat negatif 1 lah kan?
Oh, so maksudnya negatif dalam vektor tu arah
ada ke kiri, yes.
Oh, okay.
Negatif and positif arah kan, ni yang ni. Okay, bila dalam vektor kena ingat ni. Ni Cartesian coordinate. Anything that move to the left, negative. Anything that move to the right, positive. Same goes up and down. Pasal bila vektor, kalau kamu tak ingat nombor, you know the concept, tak ada masalah pun, tak payah tulis bawah ni. You dah tahu 1 ke kanan, 2 ke kiri, arrow kiri lagi panjang, so result dia arrow ke kiri. Berapa panjang arrow, the difference between these two. Same goes atas ke bawah. If it goes upwards, it will be positive lah. Positif 5 kat sini. Saya tak nak positif. Pen minta nyawa. Okay. So you go positive here. Bila kita buat composition, it is adding kan. Positif 5 add dengan ke bawah, negatif 3. Jadi kita dapat 5 tolak 3. So result dia 2. Bila kamu nampak result macam ni, positif, automatically you know the arrow will be pointing outwards. Katalah kita ada lagi satu, kita ada macam ni. Ke kanan 3 cm plus dengan ke kiri katalah 2 cm. Jadi kita ada 3 plus dengan negatif 2. Result dia 1. So you know dia akan ke positif, ke kanan. Panjang dia daripada ekor sampai kepala it will be 1 cm. Kalau atas bawah pun sama lah. So these figures, okay, positive, negative, it's just to show you the direction of the arrow, because this is vector composition. Sama ada dia turun ke naik ke, ada macam tu. Okay, this is vector composition. So jawapan dia yes, the figures is actually to show the arrows. If the arrows is negative, kalau case horizontal, arrow pointing to the left. If the case is positive, horizontal, arrow pointing to the right. If the case negative, vertical, arrow pointing down. If the case positive, vertical, arrow pointing upwards. Ni vector composition yang straightforward. Okay, dia jadi tak berapa nak straightforward when you try to have different direction of arrow. Okay, one is vertical, one is horizontal, another one is vertical. Di sini pun kita boleh tambah. If you take a look, if you follow what we have learned from the beginning, adding on is we add on based on the length, based on the direction. Jadi kalau kita ada dua macam ni, okay, what you are going to do is, katalah ni 3 cm kan. So you are going to have a 3 cm or horizontal arrow, and then katalah ni 2 cm. So you are going to have from dia punya head ni, okay, head to tail. Tail naik ke atas. Head to tail sambung dia. So ni 2 cm. Same as the figures. Jadi resultant ni, this is not the answer. The answer is the resultant, which is we go from tail, okay, tail mana yang ada dengan head mana yang ada yang kosong. So you are going to have a line there, and these are dia punya resultant. That are the answer if the composition involving multi-directional force. Maksudnya kalau kita sepak bola tu, kita bagi force ke depan, at the same time kita bagi force ke atas, result okay, kata bola ni kan, kita sepak, kita punya assumption, kita sepak macam ni lah. This is our assumption. It cause the ball to travel macam tu. Okay, tapi this resultant is actually produced by two force, a force forward, a force upwards. Okay, jadi hasil dia, since force forward is larger than force upwards, kita boleh nampak much what we call it, a longer horizontal distance compared to vertical. Katalah dia bagi yang kedua kan, dia bagi macam ni pula, 5 cm, lepas tu kita bagi force, we give horizontal force plus 2 cm. So we know the answer will be, okay, itu yang pertama dulu, 5 cm. Okay, and then yang dua ni kita nak masuk mana? Yang dua ni kita nak masuk mana? It will start from tip. Okay, from head ni ke depan. Macam tu. Jadi hasil dia from the exposed tail to the exposed tip, sambungkan. That is the hasil. Means if we give this kind of force to a ball, it will cause the ball to travel up, longer to travel compared to horizontal. Ni resultant dia. So when we have multi-directional vector to be composed, first kita tengok dulu dia punya bentuk. Okay, katalah kita ambil lebih pada 2. Okay, kita ada 1 plus 2 plus 3 plus 4. Katalah 2 cm, 2 cm, 3 cm, 4 cm. Hasil dia, start yang pertama 1, 2 cm. Lepas tu kita ada yang kedua, from tip dia, okay, turun yang kedua. Lepas tu kita ada yang ketiga, from tip dia, yang ketiga. And then yang keempat, from tip dia, yang keempat. So resultant dia, from exposed tail to exposed tip, sambungkan. Ni cara dia. This is the resultant. This is how you compose vector algebra. Okay, ni bila kita campurkan force dalam direction yang berbeza-beza. So you are going to get ni resultant ni, maksudnya if we able to measure the force in different direction, this is actually the thing that you see is like that resultant. Benda yang kita nampak. Tapi sebenarnya benda yang kita nampak tu is a combination, composition of multiple direction of force. Ni force, vector composition. Okay, this is what we call vector composition. If it is in the same, we call it direction. Okay, horizontal, vertical, tambah je terus. If it involve multiple direction, but the type is equal, okay, horizontal, stay horizontal, kita akan tengok siapa panjang, siapa pendek. It depends on the length. So, if the length is longer, they are going to dominate the direction. Tapi kalau tak nampak sangat, macam mana nak buat bentuk ni, nak length ni, tak faham, you put figures. Katalah ni 1 cm. So, we put it negatif 1 ke kiri. Campur dengan positif 2. Jadi hasil dia positif 1. Okay. And the last one is when the vector is in different direction totally. We have horizontal, we have vertical, we have diagonal. Jadi apa yang kita akan buat, kita akan ikut satu-satu. Jangan skip lah, nak lukis ni dululah. No. You start with the first one. Okay, and then from tip dia, kita sambung dengan tail yang lain. Bila kita dah sambung semua vektor macam ni kan, satu, okay, this is the first one, and then second one downwards, from tip, okay, tip to tail, tip yang lama, tail yang baru. We go to the second one, and we go to the third one. Bila dah habis tiga-tiga ni, and then only you pick exposed tail and exposed tip, kita sambungkan. So, the new resultant head will always at the tip of the last one. Ni kita panggil sebagai vector composition. Means, if we apply this kind of force to the system, it actually cause the system to move diagonally. Okay. Lepas tu kita ada vector resolution. Okay. Operation that replace a single vector with two perpendicular vector, such that the vector composition of the two perpendicular vector yields the original vector. Yang ini untuk kamu tahu sajalah. Okay. Dia adalah terbalik daripada yang ini. Dia terbalik daripada ni. Yang ini kita add on vector in order to get resultant. Okay. But vector resolution, they give you resultant. You need to find out dia punya x and y. Okay, you need to find out dia punya x and y. Ini untuk kamu tahu je lah. Dia akan bagi, most of the time, it will be in the middle. And when we talk about a resolution, it always involve just two direction of force. Dia tak ada 3, 4, 5, lepas tu multiple tak ada. Dia 2 je. Maksudnya kalau kita bagi x and y in this kind, it will move more on vertically rather than horizontally. Okay, dia macam tu je. Resolution. Yang ni pengetahuan ni. Okay, vector composition tu kita kena faham. Alright. Okay, before we go here, any question? Centripetal force. Ada apa-apa soalan? Ada soalan yang kita kat sini? Any question guys before we go to centripetal force? Ada? Tak ada? Tak nak ada?
Tak ada je.
Okay, ni MV square ni dekat atas R. Okay, bergali lah. Centripetal force is this one. FC equals to MR square over, MR pula, MV square. MV square over R. Sekejap Okay, untuk faham centripetal force ni, kita tengok contoh yang ini. Ni. Okay, Riska Physics. Alright. Saya dah share ke belum? Okay, untuk kita cerita centripetal force, I need you to we are going to discuss based on the physics of racing. Okay. Katalah kita ada, kalau tak racing pun jalan raya biasa kan, kita ada macam ni. This is your car. Okay. Now I need you to choose which is much easier. Jalan A or we go wide. Kita pergi wide, pergi buka lagi besar. Okay. If we compare A and B, which is going to be much easier in term of effort? A ke B? Yang mana effort dia lagi kurang? Right.
A.
A. Okay. Somebody say A. Alright. So, in the concept of centripetal force, it is a force, katalah ini curve kan. So, in the middle of the curve, we are going to imagine that is the axis of rotation. So, the concept of centripetal force is a force that being applied inwards. Ni centripetal force. Okay, equals to mv square over r ataupun mr omega square. Okay, so if you have quite a tight turn yang kecil, tajam, this one is going to have more centripetal force. Katalah kita namakan dia centripetal force A. This one centripetal force B. So FCA is larger compared to FCB. Okay, jadi yang lebih kecil ni lagi banyak centripetal force needed in order to keep on the curve, since the force the tangent force ataupun the linear force is larger. Okay, so centripetal force ni kalau kita buat dalam bentuk putaran, force inwards. If the force is less, apa yang kamu akan dapat? Kamu akan dapat curve yang macam ni. Katalah kita ada satu curve yang bentuk dia tak sekata. So there are part, okay, where the radius is large. There are part where the radius is small. When the radius is small, means that the force that pull the thing inwards is larger compared to yang ini. Yang ini force yang pull dia ke dalam kurang, resulting more apa ni? More wider sphere. Dia dah tak dapat sphere yang cantik macam ni. Ni sphere yang cantik lah ni. Dia dah tak dapat sphere yang macam ni. Okay. So if the force here, okay, if you take a good look at this force, this is actually the force that cause radial acceleration. Okay, AR. Jadi if FC ni kurang, centripetal force kurang, the curve of this sphere is going to be larger and larger. And that is the reason why kadang-kadang the action is not going to be smooth. Dia ada jagged. Ada tempat smooth, ada tempat bergigi. It is simply because the centripetal force is inadequate. Okay, contoh lain kita ambil macam baling tuku besi. Okay, we have a person rotating at high speed in order to throw the hammer. Okay, jadi dia akan rotate. You're going to notice if we take a look at the a video of person rotating, dia tak rotate setempat. Instead dia rotate macam tu. Tapi ada orang rotate dia cantik. Ada orang dia dah jadi unequal. Supposedly it is linearly forward, but now dia dah jadi dipping. This is because of unequal centripetal force. Okay, and it caused by the pulling action of the person to the hammer. Dia yang tarik. Jadi ada masa dia lepas, ada masa dia tarik. Ada masa dia tarik tu kuat. Ada masa dia lepas, dia dah tak larat nak tarik, dia lepas. So when dia lepas, the weight of this hammer is going to move upwards, so centripetal force is lost. Means you are not going to get a good curve. Mungkin dia akan jadi lonjongan. Okay, dia akan jadi lonjongan. Lonjongan tak equal because the center of rotation keep on moving according to the weight of the hammer. Why? Because the force is not ample to resist the tangent acceleration of this hammer. Jadi dia jadi lonjong macam ni. So, in order for you to get quite a good curve, you need centripetal force. Okay, contoh kita tengok contoh pengiraan centripetal force. Alright. Ni apa ni? Ini centripetal, Centripetal Force, FC. Okay. Contoh, kita ada sling negligible weight. Okay, kita ada centripetal force FC equals to mv square over r ataupun equals to mr omega square. Betul tak? Mr omega square, is it? Mr ataupun mv? Mr omega square. Okay, so let's say we have a case of a person swinging a hammer lah macam tadi. He swing a hammer. Okay, this person swing a hammer with a sling. Okay, maksudnya dia punya radius of rotation, dr equals to 0.75 meter. And the weight, okay, the weight of the hammer, the mass, this one is the weight of the hammer is 9 Newton. Okay, ni Newton, maksudnya dia weight. The weight of this hammer is 9 Newton. And the centripetal force, in order to keep the rotation, noted to be FC equals to 220 Newton. Okay, now the question is, at the instant of the sling being released, what is the velocity of the sling? Tu contoh pengiraan dia lah. So we have FC equals to mv square over r. Kenapa kita tak guna omega? Because there are no information regarding angular velocity kat sini. Dia tanya kamu initial linear velocity of the sling after being released. So we have 220. The mass of this object, ni weight. So kalau mass, apa yang kamu kena buat is 9 need to be divided with 9.81 first. Okay, and then we have v square. We don't have the v yet. And the r is 0.75. This one will be set to the left. So we have 0.75. We have 165 equals to 9 over 9.81. We have 0.92 v square. So the v is 165 over 0.92 and the square root of it. 165 bahagi 0.92. The answer will be square rooted 13.39. 13.39 meter per second. Ini antara contoh-contoh pengiraan based on centripetal force. Okay, and how we want to play around with centripetal force. Okay, let's try another one. Again, hammer, swinging hammer. Okay, let's say we have a hammer, and the mass of this hammer is 7.27 kg. The radius of the rotation for this hammer is 1 meter, and the linear velocity when this hammer being released, the linear velocity of this hammer is 28 meter per second. Meter per second square lah. Meter per second. Okay, so the question is, for sure we are going to have people swinging the hammer. Okay, what is the reaction force? Okay, find out force acted upon the player. Okay, acted upon the athletes just before release. Berapa force yang athlete ni endure in order to release the hammer? Okay, so benda ni sama je. Berapa dia endure sama juga dengan berapa centripetal force, because based on Newton's third law, this is what you give, you get back lah. Okay, the amount of centripetal force is actually the same amount as the force being absorbed by the players. So kita pakai formula yang sama. FC equals to mv square over r. FC kita tak tahu. We try to find out FC. It will be 7.27. V will be 28 square, and R will be 1. Direct forward je ni. Okay, 28 square times with 7.27. We have 5699.6. 5699.6 Newton. Or we can simplify this to be 5.699 kilo Newton. These are the amount of force needed in order to keep that hammer rotating and achieve that speed. Ni centripetal force. Jadi kalau kita tengok kat sini, what is actually a centripetal force? It is a force. Okay, it is actually a force being subjected to angular motion in order to keep that kind of speed, that kind of rotation. Means if we reduce this amount of force, you are not going to get this amount of velocity. Dia akan jadi lain, dia akan berubah. To centripetal force. Okay, up until there, do you have any question? Centripetal force tu ada soalan? Wih, senyap, sepi. Any question?
InsyaAllah boleh sir.
Okay. Kita berhenti kat moment of inertia. Saya habiskan moment of inertia je. Nanti yang lain ni, apa ni? Angular momentum semua kita sambung kemudian. Okay. Moment of inertia. First, when you go for any physics equation, when you see moment of, kadang-kadang ada moment of inertia, kadang-kadang ada moment of force or whatsoever. Moment of ni je meaning angular motion. Okay, and then inertia tu is talking about mass. Jadi, now moment of inertia is mass in angular. Okay, mass in angular. Alright, I need you to watch this video first. Kita tengok apa itu moment of inertia, and I'm going to explain it later. Moment. Okay, let's watch this.
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotational inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Harder. Woo! Woo! Okay. You see?
Okay. So based on that, what I'm going to show you is actually what we are going to say is, if let's say okay, let's say we have a box. This box is 10 kg in mass. Kalau kotak ni, okay, kotak ni kita tolak, it will still 10 kg per mass. Okay. Kalau kita tolak daripada atas, it also 10 kg in terms of mass. If we push diagonally, it also 10 kg of mass, because all of this action is linear action. But when the same kotak we attach to tali, okay, and we rotate the kotak, and this tali or the radius change 10 kg. 10 kg. Although the mass of the box is actually similar, but A, B, and C, in terms of moment of inertia, in terms of weight during rotation, is going to be different. Dia bukan lagi 10 kg. It will be more, it will be less. Okay. So that is moment of inertia. Okay, moment of inertia ni, inertial property of a rotating, it is actually mass. Okay, it is actually mass being distributed upon the axis. Okay, so moment of inertia, we can write it as I equals to, sometime you are going to see macam ni, mr square. Sometimes you're going to see mk square. These two is radius. Okay, yang R ni kita panggil dia sebagai radius of rotation. Yang K ni kita panggil dia sebagai radius of gyration. Okay. So to understand these two first, rotation, when we talk about radius of rotation, ini kita panggil sebagai radius of rotation. Okay, because it is fixed. It does not change. Okay. However, in human, most of the time, our movement change. The shape of the peripheral change. Contoh macam ni kan. Kita ada kaki, dua-dua kaki, kaki kanan, kaki kiri. But in position A, the mass of this complex is going to be lesser compared to B. Okay, dia tak sama. Bila manusia kita akan pakai radius of gyration because it change. Okay, but in a solid state equipment, in a solid state object, the radius does not change. Kayu ni kalau kita bengkokkan macam mana pun, the length is going to be similar. Kecuali dia patah. Tapi kaki kita, badan kita, there are tendency to change in term of COG. Jadi dekat sini COG dia tak berubah tempat, and you are going to use radius R, mr square. But in human, kita akan pakai K, mk square, because the length between COG for every single part is going to change accordingly to movement. Means movement bengkok, COG dia berubah tempat. Movement tegak, COG dia lain. The length of the COG between the length between the COG and the axis of rotation. Kalau untuk solid state, length takkan pernah berubah. Okay, kita akan ambil length daripada titik tengah berat ke axis of rotation. Okay, kita kembali kepada kotak tadi. Alright, now let's try to find out what is the moment of inertia for A. Okay, kita try cari IA, IB, IC. Okay, let's go first with IA. Mass 10, R dia, katalah ni R dia 1 meter. Yang ni R dia 3 meter. Yang ni R dia 0.8 meter. Okay, so we have 1 square and you are going to get 10 kg m moment of inertia. Moment of inertia, kgm square. Okay, IB equals to 10, 0.8 square. Okay, berapa ni? 0.8 square by 10, 6.4 kgm square. And IC equals to 10, 3 square. So 3 square will be 990 kgm square. Nampak? Kotak sama je. The kotak is actually the similar box. Okay, the kotak is still similar. Yet, if the radius is shorter, you are going to get the least weight. Ni video tadi tu, when they put the weight near to the body, so they change the radius of rotation to be smallest, and you're going to notice that the spin is going to be faster, simply because less effort is needed in order to spin that man, compared to when they put the object further from the body. Part ni, further from the body, it become heavier, although the mass of the box does not change, 10 kg. Okay, tapi bila kita jauhkan dia daripada radius, it become 90 kg. The perpetual, the sense of feeling is changed. Ni moment of inertia. And why moment of inertia is quite different from mass? Because when we talk about mass, it is solid, it is unchangeable. Kereta berat 1000 kilo. That is the mass. But if the kereta we ion that, the weight is going to be more. Instead of 1000 kilo, mungkin dia jadi 2000, 3000 kilo based on the radius of rotation or the radius of gyration. Sama macam case kaki tadi. Kita ambil case kaki tu. So we have this kind of leg, and lagi satu kita ada macam ni. Okay, this is the axis of rotation. Okay, now let's assume. Okay, peha berapa berat peha? 10 kilo. Okay. Tight equals to 10 kg. And then kita ada lower leg. Lower leg equals to 5 kg. And then kita ada feet equals to 1 kg. Okay. Regardless of shape, both of this is the same person. Jadi tight ni 10 kilo, tight ni pun 10 kilo. Okay. Now let's try to find out summation of moment of inertia for A and summation of moment of inertia for B. Jadi kita ada tiga bahagian. Okay, kita ada middle of tight, middle of lower leg, middle of feet. Same goes here. Middle of tight, middle of lower leg, middle of feet. Okay, now let's assume again. From middle of tight to the axis of rotation, that is roughly around 15 centimeter. From this bending lower leg to the axis of rotation, the axis of rotation there. Okay, this one may be around 45 centimeter. And from the feet to the axis of rotation, this one may be 1 meter. Okay, so yang ni akan jadi 0.15, yang ni akan jadi 0.45, and the last one will be 1. Okay, here, this one does not change. It is 0.15 cm. But for the lower leg, now it is longer. Okay, it is longer. Maybe here we have 0.8 meter, 80 cm. And towards the feet, we have 1.1 meter. Tiga benda yang berbeza. Okay, so let's find out the what we call it, this moment of inertia for A. Okay, jadi kita ada tiga portion kan. Kita akan cari moment of inertia tight plus moment of inertia lower leg plus moment of inertia feet. Okay, jadi apa yang kita dapat? So we have weight of tight 10 kg. 10 plus dengan R dia 0.15 square plus, okay, lower leg we have berapa berat dia ni? 5, and then dia punya radius will be 0.45 square, and finally we have feet 1 kg plus 1 square. Okay, and as for here we have summation of moment of inertia B. We have the first column. Okay, weight is the same. Mass is the same. 10 kg, 0.15 square plus, okay, lower leg, the weight is the mass is similar, 5 times with 0.8 square, and finally is the lower leg. We have 1 kg times 1.1 square. Okay, cuba kita selesaikan satu-satu. 0.15 square times 10, 0.225. Okay, 0.45 square times 5, 1.0125. And the third one, we have 1 plus pula. We don't have plus kat sini. 1 square is 1 times 1 plus 1. So kita dapat berapa total dia? 1 tambah
3.2.
Berapa?
3.24.
Kamu dah dapat. Mana dapat 3?
Salah ke?
Salah lah. Ke saya salah je? 15 square.
Oh, last tadi yang saya tambah.
Dia kosong. Betul lah. So kita tak dapat 3, kita dapat 2. 1.0125 campur 1. 2.2375. 2.2375. Okay. And moment of inertia kgm square. Okay. And then untuk yang kedua ni, okay, yang ni sama, 0.225 plus 0.8 square times 5 we have 3.2 plus 1 point, and lebih ni 2 point lebih ni. Bedal je saya ni. 1.21. 1.21. Okay, so let's 3.2 plus 0.225. 4.635. 635 kgm squared. Nampak? Two configuration of leg, the same leg, okay, the same leg, but during rotation, it does not give the same weight, the same mass. Jadi bila kaki tegak, the mass is larger compared to when you bengkok, simply because of the radius of gyration. Okay, means if the radius of gyration is small, the tendency for you to get a faster movement is increases compared to when your radius of gyration is large. Ni pergerakan dalam angular. Okay, it change. Okay, that is that is actually why if you try to swing your leg straight dengan you try to swing your leg bending, you're going to feel that straight required more force, or the straight swing going to actually take much more time to complete. Nampak macam perlahan. Kaki sama. Simply because of moment of inertia. Okay, so we are going to stop here.